Number 10 reads, a laptop computer uses a rechargeable 28-volt battery. A transformer, that black box that you plug in, is used to convert an electrical outlet's 120 volts to 28 volts. Okay? So we're going from 120 volts down to 28. Okay? Part A, if the primary coil has 370 turns, how many turns does the secondary coil have? And then part B, if the primary coil is 1.11 amperes or amps, what's the current in the secondary coil? A hint is you can calculate the power, or we'll just use our transformer equation. Okay? So this is a 4-step problem. Let's make a sketch of what's going on here. Okay? Step 1, we make a little sketch. All we're doing is we're trying to run a computer. Okay? And when you plug in a laptop or whatever, okay, into the wall, there's this little box, right? Little black box usually that you use to plug in. And this black box here, this is your transformer. Okay? How do you make a transformer? It's really easy. Inside this box, the transformer is made out of an iron core. Okay? So I'll just sketch it out in the blue here. Why iron, by the way? Iron is a special metal that's what? It's ferromagnetic. We even call it ferromagnetic for iron, right? Iron was one of the first substances that people figured out. You can align the domains, the electrons that spin that are unpaired in the same direction by either heating it up and pounding it in the same direction or stroking it with a stronger magnet, putting it in an electromagnetic field that lines up all the domains. Then all you do is you wind coils of wire around one side. This is called the primary side. And then you wind coils on the other side. And in this case, we're going to have a step-down transformer. We're going to have less winds on the output there. Okay? And next, we're going to look at what data they give us. Okay? It's a 28-volt circuit, and when you plug into the wall in America, it's 120 volts. Okay? So is this a step-up transformer or a step-down? It's a step-down transformer. Okay? And in fact, if you just look at your little laptop or your cell phone charger, it usually says right on there, okay, what kind of transformer it is, okay, what kind of input you put in, what kind of output you get. So in step 2, let's go ahead and list all this information, okay. V1 is 120 volts, V2 is 28 volts, and we're going to figure out the ratio of our step up to step down transformer there, okay. Okay, continuing. We're given N1, which is the number of coils on the input here. And let's see, what was the number of coils given? There was 370 turns, okay? That's the number of coils. And there are no units. It's just the number of coils or turns, the number of wire wraps there, okay? 370 here. And the question is, well, how many are over here? That's N2, okay? And if you actually take apart a transformer, that's what you would see. You would see an iron core with 2 windings of coil, okay? In a step-down transformer, the ratio of the turns is the ratio of the voltages. So our equation, which was given in chapter 29, is the ratio of N2 to N1 is the ratio of V2 to V1. Okay? You can actually write it the other way around, but in this case, I like to arrange it this way because this is a step-down transformer. So in other words, this transformer, or you know what? Maybe we should do it how your book has it because you can look at it either way. This might be easier for you guys. We'll do V2 to V1. Sorry, V1 to V2 is N1 to N2. It doesn't matter, okay? So when we shove in the numbers here, the whole point is this is a step-down transformer. So we go from 120 volts and we drop it down to 28 volts, okay? And that's going to be equal to the ratio of the coils. So N1 is 370. N2 is going to have less coils. Well, how many less? We'll find out in a second, okay? So if I get out my calculator, I'll just plug and chug. This is going to be 120 to 28 divided by 28. This is a step-down transformer of 4.29 or so. So in other words, I'm dropping the voltage by about a factor of 4.3 is the way you can look at it. Okay? So I'm going to end up having 4.3 less ratio of coils. So 4.28, whatever, 4.29, I'll round that off, is equal to 370 over N2. So we can solve for this by bringing the N2 up. If you cross multiply, maybe that's the easier way to look at it. N2 times 4.29 is equal to 370. So all it is we're just taking 370 over that 4.29. Okay? So in other words, the ratio of the coils is the ratio of the voltage. So in other words, if I want to drop the voltage by a factor of 4.29, I just have to divide 370 by 4.29, and on my output coil, I'm only going to have like 86.25 turns, okay? About 86.25 coils. So in real life, they would just wind it like 86 times, close enough, okay, to drop the voltage there. So that was part one of the problem there, okay? Part one. We figured out how to drop the voltage, okay? So what's nice about AC power is you can step up or step down the voltage very easily. So at a power station, what's kind of cool is they'll kick the voltage super high and then send it over, okay, big power lines there. So theoretically, actually, if you set up a coil of wire, you could actually try to steal power there, but that's, you know, unethical there, right? But anyhow, have you guys seen these on the telephone poles? Okay, guess what's inside there? There is a step down transformer to drop it down for your neighborhood, okay? And then the city of Hinsdale, actually any city, there's usually a power station surrounded by barbed wire because, you know, it's electrocution hazard. It's dangerous, but also if there was a terrorist strike, you could take out a whole town there, right? And those are just step-down transformers to drop it down to 120 volts for your neighborhood, okay? So Tesla was a genius. He figured out how to generate power and then distribute it everywhere. But the trade-off is you don't get something for nothing. So you can almost guess, okay? If you're going to get more or less voltage, the trade-off is, what are you going to trade off there? It's current, exactly. Power is equal to, it even says, here's a hint, power is equal to current times voltage. So the trick is, if you get more volts, you're going to have less amps. If you have less volts, you can have more amps, okay? So we could do the power equation, but we're actually going to be a little lazy. We'll use the transformer equation there, okay? So it says if the current in the primary coil is 1.11 amperes, what's the current in the secondary coil? So using common sense, since we ended up with less voltage, we're going to end up with more amps is the trade-off there, okay? So anyway, we'll just plug and chug here. So in part two of the problem, everything is the same, so we don't have to redraw the sketch and all that. We're just going to relist our knowns and unknowns, okay? So what they gave us was N1 was 370 turns on the coil. You solved for N2. It's a step-down transformer. We got about 86.25 turns on our coil. They give us I1, which is the current that we feed into the primary coil. That's 1.11 amps. And you're going to solve for I2. Okay? It's how much current is coming out of your transformer. So when they build a charger for like cell phone, iPod, whatever, okay? Normally people don't care. You just want to plug it in. As long as your iPod runs, okay? Yeah, you're happy to, right? You got your music. But in real life, if you don't calculate your power correctly, you're going to fry your iPod. You either give it too many volts or not enough amps or vice versa, okay? So it's kind of a scam because if you buy a charger for a cell phone, like it can be like, you know, 30 to 40 bucks. For our laptops, it's a ripoff. These things break all the time, so always trying to like buy replacement ones. I think when they first came out, these were like 80 bucks. What a scam, right? And then we found generic ones for $12. And all it is you just match the power rating, and it's power's amps times volts. P equals IV, right? A watt is an amp times a volt. So as long as we match the correct power rating, we got them as cheap as $12. Yay. Okay? So anyway, plug and chug. So what's different here is the ratio of the coils N1 to N2, okay, is equal to I2 over I1. Current is inversely related to the number of coils, okay? So in other words, if you think about it, remember when we had our electromagnet yesterday where in our generator, when we turned the crank, the magnet rotated through the coil, it generated voltage, the light bulb turned on, right? If you have more coils, you're going to have more voltage. But you're trying to push more electrons through more coils, you're going to have less current coming out, is kind of the idea. So it's a reverse ratio when it comes to current. So now when we plug and chug all the numbers, okay, we'll get our final result in step 4. N1 was 370, N2 was 86.25. In other words, this is a step-down transformer. I1 is, I2 is what we're solving for. I1 was 1.11 amps, okay? So if we do 370 over 86.25, we're going to get our ratio of 4.29, right? Because it's a step-down transformer. And then we multiply then. Yeah, we're just switching the numbers around, exactly. We're multiplying by 1.11. We'll bring it up to get our current. the current's going to go up. It'll be 4.76 amps should be good enough. Okay? So the whole point of this is a transformer makes it convenient to turn voltage from one form to another, and then the trade-off is you swap current. Okay? Now in real life, transformer actually gives you less energy overall because it's not going to be perfect. Okay? It's not going to be 100% efficient. So what actually happens to these black boxes that you plug into the wall after a while? What do they feel like? Actually, can feel it right now. They get a little hot. They get a little more warm. Okay? So transformers are not 100% efficient. They might only be like 90%, and there's energy wasted to heat. Okay? So maybe you've heard of the term called the vampire load, where if you have a lot of these chargers plugged in at home, you're wasting watts in power. Well, you're heating up your home for free. Yay. So in the winter, it might not be that bad. But in the summer, you're generating excess heat. So you can actually buy a power strip that senses when you're not charging, and it'll shut off the entire power strip. Okay? So transformers are pretty simple, and the math is very easy, but the idea is you're swapping current for voltage. And that's number 10. And then